Rehabilitation of road pavements to enhance the durability using high-strength concrete, H.S.C. Abstract. The vast amount of civil infrastructure in India includes an extensive stretch of road networks. From an economic point of view, it is more cost-effective to maintain the already existing pavements rather than building new ones. Rapid civilization leads to construction of thousands of buildings in urban areas. Nowadays, multi-storied RC-framed structures are common in urban regions in the cities like Hyderabad, Bangalore, New Delhi, Chennai, Maharashtra, Pune, etc. Due to thickly populated urban regions, the buildings are extending vertically or going high or becoming more slender. Decades are evident that traffic volume in urban regions is high when compared to semi-urban or rural regions. A large proportion of the traffic delays on these road networks are caused by road closures and closures of individual lanes for pavement maintenance purposes. The application of early-strength concrete in pavement maintenance measures will lead to a substantial reduction in the user costs involved with the road closures caused by such maintenance. These costs involve both the actual costs of the delays in terms of time and fuel consumption, but also, more importantly, the social and economic costs associated with the safety hazards resulting from these closures. This research is aimed at selecting 2 4-hour mix designs out of a total of 5 mix designs selected in a report made by Construction Technology Laboratories Incorporated, CTL, based on concrete compressive strength and freezing thawing durability. The targeted concrete strength aimed at is a minimum of 14 MPa at 4 hours. Chapter 1, Introduction. General overview. All civil infrastructures have a definite lifespan. In other words, all structures are designed to fail at some point, and this includes the vast network of road pavements in India. Approximately 2% of lands in India are paved. This consists of flexible, rigid, and composite pavements. In order to ensure that pavements achieve the purpose for which they were designed, they ought to be maintained regularly and at very little cost to the road user. Road maintenance and rehabilitation form the largest percentage of this figure. It is therefore necessary to curtail the high cost of maintenance to road users by developing measures to decrease traffic delays during maintenance and rehabilitation. There is a wide perception that concrete pavements cost too much, take too long, or are too difficult to repair. However, to the contrary, although the initial cost of concrete may be higher than for asphalt pavement, however, concrete costs less during the pavement's life cycle. Roads can be opened faster than ever and can be repaired easily with the proper equipment, materials, processes, and/or procedures. Also, concrete pavement restoration can return a pavement to a near-new condition at a lesser cost to the road user if measures to decrease delay time are put in place. Background information. Deteriorating asphalt and concrete pavement infrastructure worldwide demands innovative and economical rehabilitation solutions. When desired, a properly designed and constructed bonded overlay can add considerable life to an existing pavement, by taking advantage of the remaining structural capacity of the original pavement. For patchwork and total rehabilitation, 2 types of thin concrete pavement overlays rely on a bond between the overlay and the existing pavement for performance. Concrete overlays bonded to existing concrete pavements are called bonded concrete overlays, BCO. Concrete overlays bonded to existing asphalt pavements are called ultra-thin white topping, UTW. Research has shown that concrete overlays over asphalt often bond to the asphalt, and that some reduction of concrete flexural stresses may be expected from this effect. These overlays have been used to address rutting of asphalt pavements. Bond strength and resistance to cracking are important for overlay performance. In many cases, these overlays are constructed on heavily traveled pavements, making early opening to traffic important. Therefore, early strength development without compromising durability is necessary. Satisfactory performance will only occur if the overlay is of sufficient thickness and is well bonded to the original pavement. The design assumption is that if the overlay bonds perfectly with the original pavement, it produces a monolithic structure. Without bond, there is very little structural benefit from an overlay, and the overlay may break apart rapidly under heavy traffic. The use of concrete overlays for pavement and bridge deck maintenance and rehabilitation has been in existence for several decades. Both unbonded and bonded overlays have been used in rehabilitation and maintenance of deteriorating road pavements. For both BCO and UTW overlays, characteristics of the overlay concrete have important implications for early age behavior and long-term performance. High-performance concrete, HPC. High-performance concrete is defined as concrete made with appropriate materials combined according to a selected mix design and properly mixed, transported, placed, consolidated, and cured so that the resulting concrete will give excellent performance in the structure in which it will be exposed, and with the loads to which it will be subjected for its design life. Forster et al. 1994. The design of high-performance concrete mixes started in the 1980s in the private sector to protect parking structures and reinforced concrete high-rise buildings from chlorides, sulfates, alkali-silica reactivity, and to curtail concrete shrinkage and creep. HPC for pavements originated in the Strategic Highway Research Program under Contract C205, where the mechanical properties of HPC were described and studied under actual use conditions. SHRP developed a definition of HPC, Table 1.1, and funding for limited field trials, which were to be followed by a substantial implementation period. Performance goals for HPC pavements included an increase in pavement system service life, a decrease in construction time, including fast-track concrete paving techniques, longer life cycles such as a 30, 50-year life, and lower maintenance costs. 1.2.1 Early strength/fast-track concrete mixes. Early strength concrete mixes are concrete mixes that, through the use of high early strength cement or admixtures, are capable of attaining specified strengths at an earlier age than normal concrete. This property is very useful in road pavement maintenance and rehabilitation by reducing delay costs to the road user. Concrete or composite pavement repair is prime for maintaining existing roads. Before the advent of early strength concrete, there was no comparison of the costs of flexible pavements to rigid pavements in both initial and operating costs. This was because the initial material costs of rigid pavements and the cost of delays due to the longer closing time during maintenance and rehabilitation were far more than when asphalt was used. Since its inception, a lot of research and development has been done on early strength concrete. Early strength can be broken down into two categories: very early strength, VES, and high early strength, HES, concrete. High early strength concrete is specified to have minimum compressive strength of 14 MPa but for a longer duration of 12 hours. In the context of our research, however, the word early is considered to be relative. The concrete mixes to be researched will be termed early strength, without taking into consideration the time and place of strength gain. These criteria were adopted after considering several factors pertinent to the construction and design of highway pavements and structures. The use of a time constraint of 4 to 6 hours for very early strength, VES, concrete is intended for projects with very tight construction schedules involving full-depth pavement replacements in urban or heavily traveled areas. The strength requirement of 14 MPa to 17.5 MPa is selected to provide a class of concrete that would meet the need for rapid replacement and construction of pavements. Since very early strength, VES, concrete is intended for pavement applications where exposure to frost must be expected, it is essential that the concrete be frost resistant. Thus, it is appropriate to select a maximum W/C of 0.40, which is relatively low in comparison with conventional concrete. With a low W/C ratio, concrete durability is improved in all exposure conditions. Since VES concrete is expected to be in service in no more than 6 hours, the W/C selected might provide a discontinuous capillary pore system at about that age, as suggested by Powers et al., 1959. 1.2.2 High early strength concrete vs conventional concrete mixtures. Rather than using conventional concrete mixtures, high early strength concrete mixtures are being used to decrease the delay time due to road closures. Unlike the conventional concrete mixtures, High early strength concrete achieves its specified strength of 17.5 MPa to 21 MPa in 24 hours or less at an earlier age, from a few hours to several days. High strength at an early age is desirable in winter construction to reduce the length of time temporary protection is required, for high-speed cast-in-place construction, rapid form reuse, fast-track paving and many other uses. The additional cost of high early strength concrete is often offset by earlier reuse of forms and removal of shores, savings in the shorter duration of temporary heating, and earlier use of the structure. In road pavement maintenance and rehabilitation, strength at an early age is beneficial when early opening of the pavement is necessary. 1.2.3 Techniques used in attaining early strength. High early strength concrete can be achieved by using one or a combination of the following techniques. 1. High conventional cement content. 2. Low water, cement ratio using type I cement, 0.3 to 0.45 by mass. 4. Higher temperatures for freshly mixed concrete. 5. Chemical admixtures. 6. Higher curing temperatures. 7. Special rapid hardening cements. The above listed techniques can be used interchangeably or combined to achieve the desired strength. High early strength gain is not limited to the use of special proprietary cements such as Type 3 cement. It is now possible to achieve early strength by using locally available Portland cements, aggregates, and selected admixtures. This research uses a combination of Type 3 high early strength cement and chemical admixtures on one hand and a low water cement ratio and or high conventional cement content on the other hand to attain early strength. Literature review. In the past, ordinary Portland cement-based mixtures were not able to achieve early strength requirement without sacrificing necessary working, placement, and finishing times. Portland cement-based concrete mixtures usually require a minimum of 24 hours and, frequently, 5 to 14 days to gain sufficient strength and allow the concrete to return to service. With the advent of various techniques and materials, it is now possible to use readily available local materials to achieve early strength. In 2001, research conducted by the University of Alabama at Birmingham, titled Design and Quality Control of Concrete Overlays, developed and tested a range of plain and fiber reinforced concrete mixes that allowed reliable economic and durable overlay construction as well as early opening to traffic. The use of a lower water cement ratio and a high percentage of normal cement was used in attaining early strength. It was concluded in this research that high-strength concrete was appropriate for opening overlay to traffic in 24 hours or less, but normal strength may be used if traffic loading can be delayed for 48 or 72 hours. Under the sponsorship of the New Jersey Department of Transportation, a unique concrete mix was developed. This concrete mix attained a significant strength of 3,000 psi, 3,500 psi, 21 to 24.5 MPa, in a period of 6 to 9 hours for use on pavement repair in high-traffic areas. FHWA New Jersey 2001-015. The use of normal Portland cement and the reliance on chemical admixtures and insulated coverings was used to attain very high temperature levels in order to attain early strength. Research into the performance and strength of fast-track concrete was done under the Strategic Highway Research Program, SHRP. This research included very early strength, VES, and high early strength, HES, mixes developed under the SHRP Project C205 Mechanical Behavior of High Performance Concrete. ZIA ETAL 1993. A literature review was conducted by the Construction Technology Laboratories Incorporated based on 11 fast-track mixes developed under SHRP Contract C206 documented in a report titled Optimization of Highway Concrete Technology, SHRP Report C373, 2003. In their review report they recommended 4 mixes for further research into early strength gain. Currently there are a couple of early strength design mixes available for pavement rehabilitation, notably among them are 4x4 mix from Master Builders. The Maryland State Highway Administration, MSHA, currently requires use of a 12-hour concrete mix for patching in heavily trafficked roadways in urban areas. This mix is required in order to achieve 2500 psi, 17.5 MPa, compressive strength in 12 hours. However, the MCHA now wants to reduce the concrete set time to allow the patch to be open to traffic about 4 hours after placing the concrete in the patch. The objective of the project is to test proper concrete material mixes both designed in the lab and in the field, for composite pavements that will allow the repaired sections to be open to traffic after 4 hours of concrete placement in the patch. A shorter patch repair time would minimize the disruption caused to traffic and ultimately provide longer-lasting composite pavements. The report by the Construction Technology Laboratories, CTL, was submitted to the Maryland State Highway Administration in April 2003. Based on this report, a proposal was to be made to the Maryland State Highway Administration to test the 4 concrete mix designs selected in the report made by CTL. From an earlier literature review study of 11 mixes, 8 mixes were considered suitable for further study, 2 used at a Georgia site and 6 used at a Ohio site. Based on the performances of these mixes during the initial trials and, considering modifications for local materials, the VES mix, the GADOT mix in Georgia, and the VES mix and the ODOT mix in Ohio were selected as the 4 trial mixes to be evaluated further as part of a laboratory study. Also included as one of the trial mix designs, was a 12-hour concrete mix design currently used in Maryland for fast-track paving, and designated as the control mix. 1.5.0 Research Objective. The objective of this research is to select two concrete mixes out of the 5 selected that will yield a compressive strength of at least 14 MPa after 4 hours of casting. The selected specimen should be able to withstand at least 300 cycles of freezing and thawing. The 2 selected mixes shall have passed both criteria. Based on the findings and recommendations of this report, another phase of this project is to be started to investigate the characteristics of the recommended mixes to field conditions. This will comprise the second phase of this project. Chapter 2, Concrete and its Constituents. 2. Introduction. Concrete is a construction material. It has been used for a variety of structures such as highways, bridges, buildings, dams, and tunnels over the years. Its widespread use compared to other options like steel and timber is due to its versatility, durability, and economy. The external appearance of concrete looks very simple, but it has a very complex internal structure. It is basically a simple homogeneous mixture of 2 components: aggregates, gravel or crushed stone, and paste, cement, water, and entrapped or purposely entrained air. Cement paste normally constitutes about 25%-40% and aggregates 60%-75% of the total volume of concrete. When the paste is mixed with the aggregates, the chemical reaction of the constituents of the paste binds the aggregates into a rock-like mass as it hardens. This mass is referred to as concrete. The quality of concrete greatly depends upon the quality of the paste, and the quality of hardened concrete is determined by the amount of water used in relation to the amount of cement. Thus, the less water used, the better the quality of concrete, so far as it can be consolidated properly. Although smaller amounts of water result in stiffer mixes, these mixes are more economical and can still be used with efficient vibration during placing. The physical and chemical properties of concrete, however, can be altered by the addition of admixtures in order to attain desirable mixes for specific purposes. 2.1.0 Basic components of concrete. Concrete is made up of various components. Primarily, concrete is made up of paste, coarse aggregates, and admixtures. The basic components of concrete are the following. 2.1.1 Portland cement. Portland cement is the most common type of cement in general use around the world as a basic ingredient of concrete, mortar, stucco, and non-specialty grout. It was developed from other types of hydraulic lime in England in the early 19th century by Joseph Aspdin, and usually originates from limestone. It is a fine powder, produced by heating limestone and clay minerals in a kiln to form clinker, grinding the clinker, and adding 2 to 3% of gypsum. Several types of Portland cement are available. The most common, called ordinary Portland cement, OPC, is gray, but white Portland cement is also available. Its name is derived from its similarity to Portland stone, which was quarried on the Isle of Portland in Dorset, England. It was named by Joseph Aspdin, who obtained a patent for it in 1824. However, his son William Aspdin is regarded as the inventor of modern Portland cement due to his developments in the 1840s. 2.1.2 Types of Portland cement. Type I. Type I is a general-purpose Portland cement suitable for all uses where the special properties of other types are not required. It is used where cement or concrete is not subject to specific exposures, such as sulfate attack from soil or water, or to an objectionable temperature rise due to heat generated by hydration. Its uses include pavements and sidewalks, reinforced concrete buildings, bridges, railway structures, tanks, reservoirs, culverts, sewers, water pipes, and masonry units. Type 2 Portland cement is used where precaution against moderate sulfate attack is important, as in drainage structures where sulfate concentrations in groundwater are higher than normal but not unusually severe. Type 2 cement will usually generate less heat at a slower rate than Type I. With this moderate heat of hydration, Type 2 cement can be used in structures of considerable mass, such as large piers, heavy abutments, and heavy retaining walls. Its use will reduce temperature rise, especially important when the concrete is laid in warm weather. Type 3. Type 3 is a high early strength Portland cement that provides high strengths at an early period, usually a week or less. It is used when forms are to be removed as soon as possible, or when the structure must be put into service quickly. In cold weather, its use permits a reduction in the controlled curing period. Although richer mixtures of Type I cement can be used to gain high early strength, Type 3 may provide it more satisfactorily and more economically. 2.2.0 Aggregates. Aggregates play a major role in the properties of concrete. Using the right kind of aggregate greatly influence concrete's freshly mixed and hardened properties, mixture proportions, and economy. Aggregates can be distinguished into two distinct types based on their particle sizes. Fine aggregate consists of natural sand or crushed stone with most particles smaller than 1/5 inch, 5 mm. Coarse aggregates consist of one or a combination of gravels and crushed aggregate with particles predominantly larger than 1/5 inch, 5 mm, and generally between 3/8 and 1-1/2 inches, 9.5 and 37.5 mm. Natural aggregates are obtained by either dredging or digging from a pit, river, lake, or seabed. Crushed aggregates are produced by the crushing of quarry rock, boulders, cobbles, or large-size gravels. Aggregates must be set to some standards in order to be most useful in engineering structures. They must be clean, hard, strong, durable particles free of absorbed chemicals, coating of clay and other fine materials in amounts that could affect hydration and the bond of the cement paste. Aggregates with low resistance to weathering should be avoided in concrete mixes. 2.3.0 Aggregate characteristics. Aggregate grades and grading limits. The particle size and distribution of an aggregate is termed grading. It is determined by a sieve analysis in accordance to IS 2386-2. The 7 standard IS 2386-2 sieves for fine aggregates have openings ranging from 150 m to 3/8 in, 9.5 mm. There are 13 standard sieves for coarse aggregates that range from 0.046 inches to 4 inches, 101.6 millimeters. Grading and grading limits are usually expressed as percentages of materials passing through each sieve. It is important to specify grading limits and maximum aggregate size because it affects the relative aggregate proportions as well as cement and water requirements, workability, pumpability, economy, porosity, shrinkage and durability of concrete. It is thus important to acquire aggregates comprised of a collection of sizes so as to reduce the total volume of voids between aggregates during mixing. Shape and texture. The shape of aggregates influences the properties of concrete mixes. Angular, elongated particles and rough textured aggregate produce more workable concrete than smooth, rounded, compact aggregates. Flat and elongated particles should be avoided or at least limited to 15% by weight of the total aggregate. Strength and shrinkage. An aggregate's tensile strength ranges from 0.21 MPa to 16.1 MPa and its compressive strength from 70 MPa to 280 MPa. This is important in high-strength concrete. Aggregates with high absorption properties may have high shrinkage on drying. Other characteristics include unit weight and voids, specific gravity, absorption, surface moisture, strength and shrinkage. Handling and storage of aggregates. To minimize segregation, degradation, and contamination by deleterious substances, aggregates should be handled and stored in an appropriate fashion by stockpiling them in thin layers of uniform thickness. The most appropriate and economical method of stockpiling is the truck dump method. However, when aggregates are not delivered by truck, an acceptable and less expensive way is to form the stockpile in layers using a clamshell bucket. Washed aggregates should be stockpiled in sufficient time so that they can drain to have uniform moisture content before use. 2.4.0 Admixture. Admixtures are additives other than water, aggregates, hydraulic cement, and fibers that are added to the concrete batch immediately before or during mixing to improve specific characteristics of the concrete. There are two types of admixtures, chemical and mineral admixtures. These, when properly used, offer certain beneficial effects to concrete, including improved quality of concrete during the stages of mixing, transporting, placing and curing in adverse weather, reduction in the cost of concrete construction, avoidance of certain emergencies during concrete mix operations, and achievement of certain properties. A survey by the National Ready Mix Concrete Association reported that 39% of all ready-mixed concrete producers use fly ash, and at least 70% of produced concrete contains a water reducer admixture. The chemical composition of admixtures vary and, since many perform more than one function, it is necessary that all admixtures to be used in any concrete mix should meet specifications and tests should be made to evaluate the effect of the admixtures on the properties of the concrete mix. The beneficial effects admixtures have on concrete are due to the following properties they possess. Water reduction in the mix. Increase in concrete strength. Corrosion protection. Strength enhancement. Set retardation. Crack control, shrinkage reduction. Flowability. Finish enhancement. 2.4.1 Mineral admixtures. Mineral admixtures are usually added to concrete in large amounts to enhance its workability, improve its resistance to thermal cracking, alkali aggregate expansion and sulfate attack, reduce permeability, increase strength, and enable a reduction in the cement content, thus improving the concrete mix properties. Mineral admixtures affect the nature of the hardened concrete through hydraulic or pozzolanic activity. Pozzolans are cementitious materials and include natural pozzolans, such as the volcanic ash used in Roman concrete, fly ash and silica fume. Fly ash. Fly ashes are finely divided residues resulting from combustion of ground or powdered coal. They are generally finer than cement and consist mainly of glassy spherical particles as well as residues of hematite and magnetite, char, and some crystalline phases formed during cooling. Fly ash improves the workability in concrete, reduces segregation, bleeding, heat evolution and permeability, inhibits alkali aggregate reaction, and enhances sulfate resistance. Because Portland cement concrete pavement is largely dependent on high volumes of cement, the use of fly ash as an admixture is important where economy is important factor. Granulated blast furnace slag. Integrating the granulated slag with Portland cement clinker makes Portland blast furnace slag cement. Its use as a mineral admixture did not start until the late 1970s. Ground granulated blast furnace slag is the granular material formed when molten iron blast furnace slag is rapidly chilled by immersion in water. 2.4.2 Chemical admixtures. Chemical admixtures are added to concrete to modify its properties. They ensure the quality of concrete during mixing/transporting/placing/curing. They are added mainly for the entrainment of air, reduction of water or cement content, plasticization of fresh concrete mixtures, or control of setting time. They are added in smaller amounts as compared to mineral admixtures. They fall into the following categories: air entrains, water reducers, set retarders, set accelerators, and superplasticizers. Water reducers. Water-reducing admixtures are groups of products that are added to concrete to achieve certain workability, slump, at a lower width C than that of control concrete. In other words, they are used to reduce the quantity of mixing water required to produce concrete of a certain slump, to reduce water-cement ratio, or to increase slump. Water-reducing admixtures are used to improve the quality of concrete and to obtain specified strength at lower cement content. They also improve the properties of concrete containing marginal or low-quality aggregates, and they help in placing concrete under difficult conditions. When these are used, the water content in concrete is reduced by approximately 5%, 30% depending on whether the reducer is high range or not. Despite reduction in water content, water reducers can cause significant increases in drying shrinkage. The basic role of water reducers is to deflocculate the cement particles bounded together and release the water tied up in these units, producing more fluid paste at lower water contents. Its effectiveness in concrete is a function of its chemical composition, concrete temperature, cement composition, and fineness. Water reducers have been used primarily in bridge decks, low slump concrete overlays, and patching concrete. Specialty admixture. These include corrosion inhibitors, shrinkage control, alkali-silica reactivity inhibitors, and coloring. They can be used with Portland cement, or blended cement either individually or in combinations. 2.5.0 Water for mixing concrete. All natural and processed water that is drinkable and has no pronounced taste or odor can be used as mixing water for making concrete if as it has no chemicals that will react with the concrete constituents to change its required properties or standards. An example of this is the use of saline water, which can cause dampness of the concrete, efflorescence, white deposits of precipitated salts on the surface of the concrete, increased risk of corrosion, rust, damage to embedded reinforcement, and damage to paint systems. It is therefore advisable not to use such water for durable concrete work, and its use is generally avoided. However, some water, which may not be suitable for drinking, may still be safe for mixing concrete. Pipe-borne drinking water supplies are generally safe for making concrete. However, if in doubt of the quality of water being used, a simple test to verify its usability is to simply make two sets of cubes or cylinders of the same mix, one with the doubtful water, and the other set with distilled water, purified water, tap water, or other drinkable water of good quality. By using the second mix as reference, if the suspected water produces concrete of 28 day compressive strengths for at least 90% of the strength of the reference set, then it can be considered suitable for mixing concrete. If however it falls below this percentage, its use will depend on how far below it falls, and the standards and use for which the concrete is to be used. IS 456-2000. IS 456-2000 specifies limits of chemicals allowed in mixing water for concrete and provides a useful guide as to allowances that have worked in practice. It is acknowledged that the quality of the constituents of a concrete mix plays an important role in the quality of the concrete. However, the best materials will fail if incorporated into a concrete mixture in an improper manner or if the concrete is subsequently incorrectly mixed or transported. It is therefore important to ensure that the batching process and sequence during loading of the concrete mixer is as important as the quality of materials that make up the concrete mix. 2.6.0 Properties of concrete. The desired properties required in any concrete mix are the following. Workability. This is the ease at which concrete is placed, consolidated, and finished. Concrete mixes should be workable but not segregated or bleeding excessively. Entrained air improves workability and reduces the chances of segregation. Proper consolidation of concrete makes the use of stiffer mixes possible. Stiffer mixes tend to be more economical and are achieved by reducing the water to cement ratio or using larger proportions of coarse aggregates and a smaller proportion of fine aggregates, resulting in improved quality and economy. Permeability and water tightness. Permeability is the ability of concrete to resist water penetration or other substances. Pavements as well as other structures depending on their use require very little or no penetration of water. Water tightness is the ability of the concrete to retain water without visible leakage. This property is desirable in water-retaining or confined structures. Permeability and water tightness is a function of the permeability of the paste and aggregates, the gradation of the aggregates and the relative proportion of paste to aggregate. These are related to water-cement ratio and the degree of cement hydration or length of moist curing. Strength. This is defined as the maximum resistance of a concrete specimen to axial loading. The most common measure of concrete strength is the compressive strength. It is primarily a physical property, which is used in design calculations of structural members. General use concrete has a compressive strength of 21.0 MPa, 35.0 MPa at an age of 28 days, whilst high-strength concrete has a compressive strength of at least 42.0 MPa. In pavement design, the flexural strength of concrete is used. The compressive strength can be used, however, as an index of flexural strength, once the empirical relationship between them has been established. The flexural strength is approximated as 7.5 to 10 times the square root of the compressive strength, whilst the tensile strength is approximated as 5 to 7.5 times the square root of the compressive strength. The major factors, which determine the strength of a mix, are, the free water-cement ratio, the coarse aggregate type, harder coarse aggregates result in stronger concrete, and the cement properties. Wear resistance. Pavements are subjected to abrasion, thus, in this type of application concrete must have a high abrasion resistance. Abrasion resistance is closely related to the compressive strength of the concrete. 3.0.0 Introduction. The previous two chapters gave a brief overview of past research into concrete as a construction material, and the essence of early strength concrete in pavement maintenance and rehabilitation. This chapter details the procedures, materials used and specifications adopted in the preparation of the concrete specimens. The various test methods and test procedures are also detailed and explained. To attain early strength, the mix designs adopted from the IS 10262, 2009, report by the Construction Technology Laboratory, CTL, made use of the following techniques. F. Use of Type 3 high early strength cement. F. Low water, cement ratio, 0.3 to 0.45 by mass, using Type I cement. F. Use of chemical admixtures to enhance workability and durability. The water to cement ratios varied from 0.3 to 0.45 depending on the specimen in question. The use of normal Portland cement, Type I, and high early strength Portland cement, Type 3, was employed with various dosages of different kinds of admixtures depending on the concrete quality and specifications required in an attempt to attain the specified strength and durability requirements. The coarse aggregate fine aggregate, and the cement fine aggregate ratio were also varied in each mix. 3.2.0 Materials. Material preparations. The aggregates were passed through a sieve to determine the gradation, the distribution of aggregate particles, by size, within a given sample, in order to determine compliance with mix design specifications. This was done using a tray shaker. Both the coarse and fine aggregates were oven-dried to establish a standard uniform weight measurement throughout the test. The dry weights of the aggregates were used in this research. The amount of water was adjusted to reflect the free water necessary for the aggregate to be used in their dry state. Figure 3.1, Fine and coarse aggregates being dried in oven. 3.3.0 Concrete mix. 3.3.1 Mix characteristics and specifications. The mix specifications obtained from the CTL report were adjusted to match the bulk saturated surface dry specific gravity and absorption of the aggregates to be used. The coarse and fine aggregates obtained from aggregate industries were found to have a bulk Ssd of 2.72 and 2.59, respectively, and absorption of 0.36% and 1.36%, respectively. All aggregates were oven-dried before use. Tables 3.2 and 3.3 show the proposed mix specifications at Ssd and adjusted weights, dry weights, based on the absorption properties of the coarse and fine aggregates found by laboratory methods in accordance with IS 2386-1963, and IS 383-1970, respectively. 3.3.2 Actual mix specifications, dry weights. To ensure that the mix proportions were exact according to specifications for laboratory testing, the dry weights of the aggregates were calculated and the water-cement ratio adjusted. The mix design obtained from the report by CTL was based on the saturated surface dry density, SSD, of the aggregates. Because aggregates vary in SSD, the absorption of the aggregates used in this research was calculated in accordance to IS 2386-1963, and IS 383-1970, for coarse and fine aggregates respectively. To find the SSD and absorption of the aggregates were oven-dried to a condition where there was no change in mass. The dry weights of the aggregates were measured and recorded. The aggregates were then immersed in water to a state where they were fully saturated. The weights of the fully saturated aggregates were measured and the absorption computed as follows. Knowing the quantity of water that the aggregate will absorb when fully saturated, the dry weights of the aggregate was computed as shown above, and the amount of absorbed water at SSD was added to the amount of free water to get the total weight of water required for the mix. Allowance was also allowed for the use of polar set, since each liter of polar set added to a concrete mix will contribute 0.78 kilograms of water to that mix. 3.4.0 Compressive Strength Test. This phase consists of applying a compressive axial load to a molded cylinder until failure occurs in accordance with IS 456-2000. The material for each mix design was batched based on the actual mix specifications in Table 3.3 above. The concrete was mixed and cured in accordance with IS 456-2000, standard practice for making and curing test specimens in the laboratory, making sure the inner surface of the mixer was wetted to compensate for the loss of free water due to absorption by the surface of the mixer. The concrete components were mixed in an electrically driven mixer. A shovel was used to scoop the mixed concrete into a large wheelbarrow, and a slump test was used to test the water content of the concrete. The cone was 1-0 high, with a top opening of 4 diameter and a bottom opening of 8 diameter. The mixed concrete was placed into the cone through the top, a bar was used to compact the concrete, and remove air voids, within the cone. The cone was then lifted clear. By laying a bar on top of the cone, it was possible to measure how far the concrete slumped. 6x12 cylindrical plastic molds were filled and compacted using an external table vibrator to remove air voids. A total of 60 cylindrical specimens were cast, for each of the 3 test conditions, 4 hours, 24 hours, and 7 days, for a total of 5 different mixes. The 20 specimens were then demolded, weighed and tested after 4 hours to obtain the compressive strength. The same procedure was repeated after 24 hours and 7 days to obtain the compressive strength after that period of placing. The 7-day-old specimen was placed in a curing tank after 24 HRS. 3.6.0 Identification of specimen. Each specimen was identified based on the nomenclature assigned to it. For the cylindrical specimen tested for compressive strength, a nomenclature of MC1A depicted mix 1, specimen A. For a specimen used in the freeze and thaw test, a nomenclature of mu1A depicted mix 1, specimen A. 3.7.0 Apparatus. General apparatus. 1 Concrete mixer. 2 tamping rod 5/8 diameter and approximately 24 inches long. 3 mallet. 4 external vibrator, table vibrator. 5 small tools, shovel, trowel, wood float, straight edge, ruler, scoop, slump apparatus. 6 sampling and mixing pen. 7 air content apparatus. 8 scale, large and small scales. 9 curing tank. Phase I. 16x12 cylindrical molds. 2 compression testing machine. 3.8.0 materials. The following materials were used for this research: type I and 3 cements, 3/4 coarse aggregates, gravel, fine aggregate, mortar sand. Chapter 4, Test Results and Discussions. 4.0.0 Introduction. This chapter reports the results obtained from the laboratory tests of the various test specimens. It attempts to analyze the results obtained and report them in a graphical and tabular format. It deals with the compression test results as an isolated criterion and then the freeze and thaw test results as another. It finally attempts to analyze the various mixes combining both criteria. The mixes employed in this research were designed to attain a compressive strength of at least 17.5 MPa in 4 hours or less. It was also expected that the mixes would go through at least 300 cycles of freeze and thaw without failing or excessive scaling. A summary of the test results is discussed in the sections that follow. 4.1.0 Properties of the concrete mixes. The property of a concrete mix depicts its strength, durability, and performance under loading. Properties affecting concrete characteristics measured in this research include the following. Air content. Consistency. When in its fresh state, concrete should be plastic or semi-fluid and generally capable of being molded by hand. This does not include a very wet concrete which can be cast in a mold, but which is not pliable and capable of being molded or shaped like a lump of modeling clay, nor a dry mix, which crumbles when molded into a slump cone. The slump test is the most generally accepted method used to measure the consistency of concrete. The slump results in Table 4.2 show that Mix 3 had the best consistency and Mix 4 and Mix 5 had the worst consistencies. This result was expected due to the proportions of water and water reducers in the different mixes. Mix 3 containing 11.6% and 0.08% of water and high-range water reducer respectively by weight of the total constituents was expected to be most workable. The opposite was expected for Mix 4 and Mix 5 as shown in Table 4.1. Due to poor consistency of Mix 4 and Mix 5, no slump was recorded for those mixes. The formed cone either collapsed totally or did not show any slump when the slump cone was removed. 4.2.0 Compressive test results. One of the most important strength-related parameters used to define the early strength of a concrete mix is its compressive strength. The average results are as shown in tables 4.3a, 4.3c below. Early strength concrete is widely accepted to be concrete that can gain a compressive strength in the range of 17.5 MPa and 24.5 MPa within 24 hours or less.